Okay. Well, we were here for round 2. And because of the request, I put up like, oh, what kind of statistical test to run? What I put together, I know it's kind of small, but it seems like the best board space I have. I put up my job talk back in 2000 and what? I started in 2006. I would have done my job talk in 2005, and I was young and spry, and I had to talk about stats, and I was all excited about this table I put together, and it got me the job, so I have a personal connection to it. But if I had to remember anything about like the kinds of basic inferential tests that could be run, so granted, when it comes to your future journal articles that you're looking at, or the ones you currently have at hand, some of them are going to do much more fancy analyses, like survival analyses or path analyses, or just other fancier stuff, words that, discriminant analyses. There's all sorts of words that, could come up, some sorts of tests that they can run. And those are the more, complicated tests, path analyses, all sorts of stuff, structural equation modeling, you name it. But these are the more basic ones, okay? And these are inferential tests, by the way. These are inferential tests, and these are the kind of tests that you would have where you would have p-values in them, to say, oh, the null hypothesis is, these findings support the null hypothesis or the alternative hypothesis that we were just going over earlier, right? One-tailed test, two-tailed test, all these apply. So when you have basic descriptive statistics, usually those might come as, so that's another thing. So this is my ad-libbing here. Descriptive statistics would be more frequencies and percentages. Descriptive, S-C-R-I-P-T-I-V-E. So remember we talked about descriptive stats being describing the sample. Well, when you think about descriptive statistics, what you have to think about is the kind of data you have at hand. Okay, so let's say I want to do descriptive statistics on the gender of this, the gender breakdown of this class. What kind of statistics? I'm talking about 3rd grade, 4th grade level statistics. I'm not talking any fancy beyond that. Okay, so what would be some descriptive statistics I would put down or I would run for gender, the gender breakdown of this class? Did I ask this old guy what it is? No? No. Put you on the spot? No. What do you think? If I had to describe the gender breakdown of this class, what kind of stats would you throw out there? I'm not asking simple stuff. The number is called the frequency. Yeah, frequency. So that's frequency. How frequent, right? That's the number. What can you do with a frequency too? What's something that you see all the time?
Out of the total number of people.
Out of the whole, which is a percent. Yeah, percent. And you run frequency and percent for the kind of data where people are broken down into categories. So that would, so I would say for categorical data, for data that's in categories. For categorical data. Tell me some kind of data that also comes in categories. What's another? So gender is a categorical variable because the answers are male or female. You fall into one of the two or other categories. What are some other categorical type of variables other than gender? What's another example that I could do categories for? Yeah,
Ethnicity.
Ethnicity, because you have races. Well, races. Yeah. Well, yeah, you know what? Yeah. So Asian American or all different nations, whatever. Yeah. That's yep. If I was doing it, yeah.
Maybe like student or non-student.
Absolutely. You fall into one or the other. Yep. Those are good. Oh, age. What do you think?
If it's like group, like
if you do age groups, right? So like sometimes when you fill out a survey in a magazine, it's like, oh, what age group do you belong to? 31 to 40, 41 to 50, 51 to 60. Oh, when you start getting into the next age group, you're like, oh, I don't like that birthday. Right? Oh, no. Okay, so age categories perhaps, right? How about if I was doing a taste test, it could be brand A, brand B, brand C, or any kind of brand of things, right? Those could be examples of categories. So you kind of get the gist, right? So let's talk about age, and I have to, God forbid, report my actual age. What statistics would I do on that? I mean, I could do a frequency and percentage breakdown, but then I'd have 45-year-olds, 46-year-olds, 47-year-olds, 48-year-olds, 49-year-olds, 40, 40, 50. I'm thinking like my daughter now. It's probably something she was saying. So what about, so I call that as continuous data, right? Okay, continuous data. Because you can just keep going on and on and on and on, right? And the data reflects actual numbers. So if I had something like age, well, basically I'm saying age is a continuous variable. What statistic would I run instead of the frequency and percent? Because I just get a bunch of gobbledygook if I did a frequency and percentage for that. What would you do if I wanted to, if I got everybody's age, okay, and put it in Excel, what would I have Excel do for me for that data?
Relative frequency?
No, you could, but to make it
average?
average, yeah, I do the mean, right? The mean. Yep, mean age. And probably along with that, I would do standard deviation as well. Why, okay, so mean age is great. I can say the average age of you guys, gals. Why would I put standard deviation in there too? Why would I calculate that along with the mean? Just any idea? Why would I care about the standard deviation? How does that influence what the data looks like? So let's say I had mean age of 35 with a standard deviation of 10. And let's say I had 35 with a standard deviation of 20. How are the people going to look in the standard deviation with a standard, same age, same mean age, but standard deviation of 10 versus standard deviation of 20? What would the class look like in each of the two groups compared to, what would you say would look different?
Like the population is going to be different because like if it's standard deviation of 10, then it's going to be more of like adults-ish, whereas if it's 20, younger
and older, right?
Yeah.
So you're gonna have little kids and, so standard deviation is an important statistic that go along with the mean. So basically, let's put it this way, percentage is good to go along with frequency because, I can have a big tally of something, but then if it's out of like a large number, 4,000 people, maybe that percentage is not gonna be that big, right? So frequency in combination with percentage gives you a nice picture of what you're seeing, right? Because what's that percentage about? So let's say I have 50 women. Oh, what does that mean? Well, okay, out of 100 people, okay, that's 50%. Okay, it's like half women, half men. So it gives me a full picture of what's going on. So that's with categorical data. And then with continuous data, it's nice to get the mean along with the standard deviation because the standard deviation tells me how diverse the population is in regard to that variable. Okay. So both percentage and standard deviation kind of gives you the extent to which diversity is there, right? If it's 99% female, it's not as diverse as in regards to gender. When it comes to a small standard deviation, or if the standard deviation was 0, it means everybody was the same age. That kind of thing, it's maybe your class, your graduating high school class or something like that. Okay. So those are the descriptive statistics you would use for data that is most common. I mean, you could add other stuff to that, the minimum, the maximum, the quartiles, the percentiles, all this fancy stuff. We'll talk a little bit about percentiles a little later. But that's some of the basic stuff. And then let's get into inferential statistics. So this would be a typical table 1 where you have frequency and percentages for your samples, means, and standard deviations. And then if you go to subsequent tables where they start running some inferential tests, if they're relatively simple ones like this, these are the simple ones, okay? You know, the kind of test that's appropriate to run, and you are very likely to run this stuff too. And one thing I want to tell you is, you know, we're talking about the appropriate statistics to run. Oh yeah, a frequency and percentage in this case, and the mean standard deviation. Well, SPSS, a program like SPSS and a lot of your statistical softwares are smart, and they could do some stuff that you can't do in your head or easily do, you know. But guess what? If I tell SPSS, you know, I work mostly with SPSS, and I do run statistics. When I use SPSS, and if I told it to run mean gender, it would run it for me. Does it mean that it's accurate, or does it have meaningful information? No, it's just a bunch of gobbledygook. But I swear to God, when I've taught statistics, I'll have people give me mean gender. I'm like, okay. And what SPSS will do is, you know, if male equals 1 and female equals 2, they would do the 1s and the 2s and take an average, and that makes no sense. Okay, so, you know, just because you run it doesn't mean it's right. I could run a frequency and percentage for age, and it would come out like this for every possible age that somebody answered, and it wouldn't be concise enough to be meaningful. So that's something important to know, is that you're smarter than your software. Even though it can do fancier stuff for you, it's like a horse that can run really fast, but you have to give it the direction. So that's an important thing to know about stats as well. Okay, and so for inferential statistics, so the kind of test you can run depends upon, you know, again, you have to do the continuous versus categorical variable thing that you have to think about, and the combination of the two. So we talked about the independent variable being the cause of the dependent variable, right? So what you have to consider is the kind of variable you have for each. So when you combine the two, you've got an independent variable an independent variable that's categorical, a dependent variable that's categorical. You run something called a chi-square test. Can you think of a chi-square kind of test sort of scenario where your independent variable is categorical, your dependent variable is categorical? Can you give me an example of one? I see my face in the back, but I'll ask one of the students to come up with something. Anybody got an idea? And we'll depict it with a little miniature graph over there in that box. I mean, I won't make you do that. I'll do it myself. But can you think of an example of a chi-square example? Continuous and continuous. Yeah.
We're doing chi-square, right?
Yeah.
Okay. It could be like coffee drinkers and smokers.
So if you drink coffee, are you more likely to smoke too? Okay. So, yeah. So what that would look like. So that's a good one. Coffee drinker, yes, no. Smoker, yes, no. You know, a lot of times if you want to, I think a lot of people drink coffee in general, but they don't smoke. But then there's probably a lot of smokers drink coffee too. So if you want to look at the relationship between coffee drinking and smoking, you would look at the chi-square test. And if I were to do a graph, if I were to do a visual on this, what would it look like? You'd probably have something, you'd have a percentage breakdown. So what would you do? Coffee drinkers, smokers. So coffee drinker, I can think about that one. So you could basically see coffee drinkers and smokers, right? So you can have coffee, yes, no, smokers, yes, no, right? So you could have these 4 bars, and you could see, and is there a pattern? Do the coffee drinkers have higher rates of smoking than the non-coffee drinkers, right? So you basically have 4 boxes of data, or 4 little bars to kind of compare. Are they all equal, or is there's you know, among the non-drinkers, there's less smokers, that kind of thing. You know, smoking rates, coffee, no coffee. And then smoke, non-smoking. Smoke, non-smoking, right? And you basically want to see if these 2 bars have the same pattern as these two bars? Or is there some sort of weird thing going on? And if there's some sort of weird thing going on, there's a statistical significance. Okay. Yes,
Can you give more examples of continuous variables?
continuous variables, what they look like in general. We said age is one. Okay, let's think of another one. Tell me. So age is something continuous. Huh? Let's see. Oh, okay, how about
Money.
money, right?
Height.
Height and weight, all those things, yeah, you could come up, so anything continuous, you could come up with the raw numbers, and it goes from low to high, right, or high to low, whatever. What else? Basically, any kind of lab result, right, when you get your, go to Kaiser, you get your lab results for your white blood cell count, and your hemoglobin count, and your, all that sort of good stuff, right, those would be continuous. Any other examples you want to think of? Temperature, absolutely. All right. So those are my ideas. Yeah. So continuous. Okay. So what if you have an independent variable that's categorical and your dependent variable that's continuous? So it's basically what you're looking at is you're comparing two or more groups on something continuous. So that's what this box is. So what are some examples where you have, and when you run those kind of tests where you're comparing groups on something continuous outcomes, you're running t-tests or ANOVA. So let's think of, so t-test will be specifically when you're comparing two groups on an outcome, and ANOVA is three or more groups on an outcome. So t-test, I'm going to say two groups. You're running differential. Well, actually, you could do a one sample t-test. So the cartoon example we did was a one sample t-test where you're comparing one group to this criterion. But otherwise, when you're doing two samples, you're comparing this group to this group. It could be paired samples where you're comparing like my group before and my group after, or it could be comparing this group to this group, which is independent samples t-tests. ANOVA is 3+ groups. Can you give me an example of something that is a t-test or an ANOVA? Yeah.
Maybe you can, like in a classroom,
Mm-hmm.
you want to check there.
Mm-hmm.
Or while the exam.
Yeah, so my daughter used to do Kumon. And what they could do is they can compare girls and boys. Let's say they all, started at a certain level and they spent a month in Kumon. And I just want to compare the boys and the girls on their scores at the end of the month, right? That would definitely be an independent samples t-test because my categorical variable is girls and boys. So what it would look like is, in this case, I'd have two bars, right? And let's say, I'm going to say boys. These boys do worse than the girls. Because they're all girls. Masculine. Masculine. Okay. Mean math score, actually. All right. And so what we're looking at, the whole point of running either a t-test or an ANOVA is to see whether this difference between the boys and the girls is statistically significant. The bigger the difference you see, the more significant it's going to be, and the p-value is going to be something less than 0.5. But if there's less difference, right, that p-value is going to be something bigger. So that's a t-test example. What's an ANOVA example? Basically same concept as t-test, but you have three or more groups. So anybody have an example? Yeah.
Maybe, like for my field, maybe like students that have hearing aids, students that have cochlear implants, and then maybe normal hearing.
Sure. And the dependent variable would be something like
Their vocabulary.
vocabulary, okay, right, very good. And so that kind of test would give people information about, what's better in terms of a hearing aid, right? Maybe not, or just some background information about how their vocabulary is as a result of being in one group or the other. Good. Logistic regression is not as easy to depict. But logistic regression is used, if it's bivariate logistic regression, it's usually like a yes-no kind of outcome. Like, let's say, for example, so this is a hard one to kind of think about, so I'm just going to give you an example. And I tend to use, logistic regression is used a lot in the literature, because if you have some outcome like death, yes or no, or got the disease, yes or no, right? And that's the outcome. And then the predictors could be of various other stuff like your age. So what are your chances of the outcome? Or it could be smoker, non-smoker. It could be, whatever it is, right? DUI, no DUI. And then there's these predictors that predict, like if you've had, okay, so I'm doing a study on DUI. Who gets some more often, okay? And so my outcome would be DUI, I've had one or I haven't, one or more. Predictors could be a variety of things. Could be like what, age. And actually with logistic regression, you could put in independent variables that are categorically as well if you want. But if you're going to put continuous ones in, use logistic regression for that. And you're going to come across quite a few studies with logistic regression where the outcome is something that's yes or no, A or B, that kind of thing. People who have to get very familiar with something like, there's more complicated analyses than that. But in a very basic case, have you ever heard of actuarial statisticians before? Do you know what they do? I know they make good money. I know that much. But what they do is they predict outcomes. A lot of times they work for insurance companies and they're trying to predict specific outcomes. Like, if they work for a life insurance company, and, basically they're looking at life or death at a certain time point, likelihood of whatever it is, certain outcomes. And they're trying to put in all these demographic factors, all these background factors. Do they have a family history of that? Do they have a family history of this? Do they smoke? Do they drink? Do they have a family history of obesity? And they use that to predict whatever outcome, which can influence how they do premiums for people based on the profile they have. So that, logistic regression is kind of the basis for those kind of analyses, which is kind of cool stuff. And then last but not least, a correlation coefficient. And by the way, when it comes to the level of analyses that you're likely to do for a project or thesis, it's a lot. It's going to be doing this stuff pretty much, for sure. And very possibly some higher level statistics, but these are the basics. Correlation. So your independent variables continuous, your dependent variables continuous. So usually you put the independent variable here, your dependent variable here. Can you give me some examples of something that you could run a correlation coefficient for? Yeah, sure. What kind of relationship would you expect between the two? Increase over time, right, as you get older, right? So what would that look like if I had to draw a line? Going up, going down, going straight out. Kind of like this, right? Yeah. Could I have some relationships between two things that are negative, like it go this way? Or can you think of something that would go the opposite direction? something where you have a negative relationship between the two things. Can you think? When it's dinner time? How about time of day? Or like, time going without eating and your concentration levels. Right? That would go the other direction, right? And so what happens is with a correlation coefficient, you run to see if it can go in a positive direction, it can go in a negative direction, or there could be no relationship, right? And what happens with a correlation coefficient, data can be plotted out. So people's data, like everybody could be plotted out here as a dot. Like every participant could be a dot. And a correlation is the extent to which, does it go up, does it go down the line, the best fitting line for the data? And it also has a function of how close the data are to that line, So if you have a really strong correlation between age and weight, it's going to look like this. So these are peeps. These are individual people. And of course, there's going to be somebody who is way over here, very heavy at a young age. You're going to have somebody who's down here, who's very light at an old age, right? Oh, what are these folks called? Do you know what they're called? Outliers. Oh, that's what they look like. They just don't follow the herd, do they? No. So that's what a correlation coefficient is. If there was a zero correlation, what would this graph look like? It'd just be basically a cotton ball. It'd just be and it's basically look like that. Okay? There would be the data wouldn't seem to come in the shape of a line at all whatsoever. So, there's a slope of the line, like how sharp of an increase there is, and also like how well the data lines up with that line that best fits the data. So, any questions so far? So that was a nice little improv. Statistical analyses, some basic things, and kind of gets you thinking about continuous data, categorical data, what kind of stats you could run for it. Right, so that kind of gives you that's some nuts and bolts about and if I was teaching an undergrad class, we'd be going over this stuff for like 4 weeks, but this was a crash course in whatever minutes before dinner. Questions about that? No? Any other? Okay, well I'll just keep going. So that's that. Let's see. Lecture summary from the last slide. Using statistics on data results in the development of evidence based in your field of study. So that's, what I would say about this. The evidence base grows and changes over time, which is true. Back in the day, when I was young, bagels were a cool thing to eat. That was healthy. But what do we say now about that? What's wrong with bagels? Bagels are still good, but still taste really good. But what do they say? Now the thing is to do what? Not bagels, but vegan or more protein, whatever, right? So the evidence changes over time. So one thing I would say, just as a graduate student, because I find myself collecting lots of data, but then I don't take the time and the energy to publish. So whenever you can, if I, whether, some of you I'm sure are going to become PhDs, always set aside time to publish your work because it could be some useful gems. I bet there's lots of useful gems. I think I have a lot of useful gems of data that I just never fully got published. So just keep that in mind to try to get that done yourself. Put time, even though it's hard to do. One thing I notice with graduate students, sometimes when they're done, they got their project done, but it's not quite ready for publication. They're kind of like, see ya, and they kind of forget it. And if you can help it, it's to your advantage to put the time in to finish it up and submit it for publication. See what happens. That's only going to increase your credentials and basically increase your qualifications for any kind of future job. If that's the best, and it's good for the science too, to contribute to the literature as well. In quantitative research, descriptive statistics are used to summarize data at hand, while inferential statistics are used to make inferences. We just talked about that. And we talked about p-values, so we can move on to the second part. Let's see. Research questions. So this is more the second wing of today is more about interpreting patterns, looking at data. The intention of today was not to go over these specific statistics, but I think it was useful based on your feedback. So that's why we did that. So we're going to spend some more time with just kind of talking about data and see what we can do with it. So let's pretend that we are collecting data on two samples of foster youth, one group who lives in a facility and one group that lives in family homes. Okay. Research question: do foster youth living in a facility differ from foster youth living in family homes on a 10-item depression inventory scale? So this is just a hypothetical thing I came up with. And these are the questions. It's a very common, the CESD depression scale is the short, this is like a short version of it. Very common, commonly used, I felt, and so these are the questions that people are asked, and it's a simple yes, no kind of answer thing. And what you can do is add up the yeses to get a total score out of 10 possible. So you can get a raw score or percentage, right? Percentage yes scores. So if I was going to compare the kids who live in the facility versus the kids who live in individual homes on depression scores, let's apply this. What kind of inferential test would I use? My independent variables, what level? I got the two groups of people, right? Two groups of people, and the dependent variable is continuous because I can add up the scores to get a total score. So I am running a t-test. I can run a t-test. So basically with a t-test, I'm comparing two means. The mean depression score for the group that lives in the facility. So I have to get a sample in each, right? So let's say I have 10 kids who live in the facility, 10 kids who live in homes, right? I'm comparing the mean score in depression for that facility group. I'm comparing, and compare that to the mean scores people who live in homes. That's an independent samples t-test. I want to see if those two groups have similar means. If they didn't, the means are different, right? Okay, so the more different they are, that p-value is going to go what, up or down? If they're different like this, the p-value going to be higher or low? Lower. And if the groups are like this on depression, it's going to be high, the p-value be higher. Yeah, I know it's counterintuitive, right? But that's just the way it works. And so what I have is this cool t-test calculator, which you can, there's these t-test, so let's say you don't have statistical software, but you have a calculator for Excel where you can calculate means and standard deviations. You don't have to have a statistical software downloaded on it. Well, actually, Excel can run this stuff too. But anyways, we're just going to play around with data. And the things I want you to look at is how big of a sample size do I need to find a statistically significant difference? Ooh, what did we say a statistically significant difference is? What's the p-value? P equals 0.05 or less, right? Okay. How much more depressed does one group have to be than another to find a statistically significant difference? So, you know, sample size is something that goes into the t-test score. So does how much different the two groups are. And another thing just to think about is how much of a difference is meaningful anyways. I mean, you know, it goes from 0 to 10. So the difference between 9 and 10, is that very, very different? Maybe not. I don't know. I'm not a clinical psychologist to know. But that's always something to think about. But anyways, let's just kind of mess around with the data here. Oops. What's on the next slide? Statistics. Okay. All right, so quick calcs. So this is just a website, and there's lots of them. You can get a chi-square calculator. There's a t-test calculator, and it asks for some basic information. And so this is one such example. It's for t-test, so that's cool. And this is for independent samples t-test. So that's why it says unpaired. Unpaired means it's just two independent groups, like men and women, or foster youth and one group in group A, foster youth in group B. Paired samples would be like me before and me after, or a group of husbands and their wives, and they're paired, right? But these aren't paired, these are independent samples. So enter data. So what did we say the range for depression scores are? So what it's asking me to do is, so I can label this. Homes, let's say, or we can say facility. And we can say homes. Okay, so give me a mean score that you want to have for facility depression score. I don't know, out of 10, what should we put down? 6. What should we put down for homes? Doesn't matter to me. 8. Okay, standard deviation, we'll keep it consistent for both, so we could say that the groups are relatively same in terms of the diversity. Okay, so I'm going to put down 2, maybe 1. 1 with standard deviation of 1 in each group. How many people do we want to have in each group? That's n. 20? Let's do 20 in each group. By the way, you don't have to have exact numbers in each group. I could even do 19 or whatever, but I'm just going to do, for argument's sake, I'm just going to put in 20. Okay, and then we could calculate now. So keep in mind, memory bank, facility 6, homes is 8, standard deviation. So what basically we're looking at with a sample size of 20, how different is 6 from 8? Okay, calculate now. Okay, and let's look for what the p-value is. The two-tailed. What does it say? The two-tailed p-value is less than 0.0001. By conventional criteria, this difference is considered to be extremely significant. Okay, so that's your answer, but let's go back. So that was significant, so we would say that it is statistically significant, but let's fool around with the numbers. Let's go backwards. Let's change this. What if I did 7 and 8? What's going to happen to the p-value? The p-value is going to increase. Let's find out how much it increases by. Ah, it went down a little bit, right? But it's still significant, right? Let me go back again. Do I want to remember? No. But I don't think so. This is, all right. What do you think is going to happen if I increase the standard deviation? What's going to happen to the p-value? So if my groups are a little bit more diverse, they're all over the place. Some are happy, 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 and some are not, not. What's going to happen? The p-value is going to increase. Let's find out. Let's quadruple the standard deviation. P-value is going to go up. Oh, it's no longer significant. So now you kind of understand how these things influence, right? So the bigger the mean difference is, the p-value is going to go down, right? When I change the standard deviation, the bigger the standard deviation is, it means my groups are more diverse to the point that somebody in the foster home group is going to look like somebody in the other group, right? Or you know what I'm saying? Okay. What else should we mess around with? We messed around with the we messed around with the mean. We messed around with the standard deviation. We can mess around with the sample size. Let's bring it down to 10. Oh, well, let's just bring the standard deviation. I'm going to make it 2. Okay. Or why don't we just keep to 4 for now? Okay. So what if I brought this to 100? What's going to happen to the p-value? Do you know? It's going to decrease, right? Because you know what happens is with a bigger sample size, you basically get more. You're basically saying, well, I have a bigger chunk of of the population. And well, yeah, actually, you know what usually happens? It's kind of interesting. So the bigger the sample size is, usually your standard deviation is going to go down because you have, the pattern is going to be there more. Well, okay, if the population is 90-something% female, it's more likely if I have a larger sample of 100 people, it's more likely that I'm going to get 9 women and 1 man versus if I just sampled 3 people and it so happens that one of them happens to be a dude. That makes, you know what I'm saying? So let's see what happens. But anyways, by just changing N and keeping everything else the same, let's see what happens. Oh, whoa, look at that. It's almost significant, isn't it? 0.0786. Interesting. Okay. So I had to get out of this. Let's get out of this. So important things to consider. So the whole thing about this, I can play around with it more if you want to, but I think you get the idea. So the important things about the t-test, right, is bigger differences between the mean equals lower p-value, right? That's one of the things that I got out of this. The bigger the standard deviation is, that's going to bring up the p-value, isn't it? If I have a larger sample size, it's going to bring the p-value down. So that's why, when people do studies, especially when it comes to grants, okay? So if you end up applying for a grant while you're in graduate school, one of the criteria that your grant funding agency is going to look at is if you have a larger sample size, because as you can tell from this exercise, if you don't have a large enough sample size, your results might not be statistically significant simply because of the mere virtue that you only had a sample size of 10 versus 100, that kind of thing. So you can use, and here's another important thing as a graduate student, if you were to run some tests and you need to figure out what kind of sample size you want to have, I would totally get this kind of calculator like this to figure out about how many people I want to have in my groups. Does that make sense? I would do that to figure out. Yeah.
I have a question about the standard deviation. You said the higher the standard deviation, the higher the p-value.
It's going to make it less significant. Yes.
Why?
Because what's going to happen is so the question was, why does a standard deviation bring the p-value up? It's because when you have a bigger standard deviation, your groups, so like if I had group 1, I can't really board space here, but if I had group 1 and group 2 and they're more all over the place with scores, like this, and you have 2 groups so they're all kind of all over the place, the more likely it is that somebody in one group is kind of like somebody in, they're less, they're less distinct because they're so all over the place with their standard deviation is why. But if you have this pattern where there's not much standard deviation, people pretty much look like this on the mean and average in this group, and this group, it's pretty much like this, right, with not too much, yeah. So I explained that with charades just now. Okay, so any other questions? What else? So we talked about sample size, right? So that's, when it comes to any kind of results you have to do, and you want to say, I want to look, and you could decide what's a meaningful difference. Is a 1-point difference between the groups meaningful, or is a 2-point difference meaningful? You could use that and just kind of plug some numbers in to kind of take a guesstimate of what would be a reasonably good sample size. Probably your advisor would tell you what they expect to have, but this is one way to kind of take a guess of what would work. Okay? Anything about that exercise? Any other questions about that exercise at all? Does this kind of help clarify what statistics looks like and how the things, yeah? Okay, all right. Let's go t-test calculator. What else? Items. Research. Oh, you know what? Here's a good question. Okay. I'm going to ask you a question. So I told you the importance of pulling up questions from the literature. This is an established thing that you could use. Do I have to use it the exact same way? Do I have to use the exact same words that they use on my survey? Do I have to say, I felt depressed, yes or no? Or can I change it up a little bit? Somebody says no, what else does somebody else say? Anybody else have an opinion? You're afraid to say, you're just tired and want to eat. But go ahead, anybody else? Yeah.
When I did my research methods class, we had to use the exact same question
Okay,
from the literature.
okay.
But we had to change, like, or add ethnicities that were not surveyed.
So the ethnicity question that you borrowed from the literature, you can't use it because you had to expand upon it because there's more ethnic groups here. Yes.
Exactly.
Okay, and these are pretty straightforward questions, so you would probably think, well, I don't need to fool around with this. This is pretty simple. I pretty much keep it the way it was. The answer is to this question that I just asked you is it depends on your population, because some questions are more complex. And if you had a different population that could be slightly younger, slightly lower, or younger, older, it could be certain cultures. So like, for example, if you were to translate this for another culture, the meaning might come out a little different, or the question wouldn't make entire sense to them the way it's worded for this particular scale. You do have the authority to change it up if there was a good rationale for it. An example of that, I've worked with Sora Siri, so she is the principal investigator of the grant that gives you this opportunity to be here for the Allied Health Academy. She's done research on Pacific Islander women, and we looked at attitudes towards cancer, beliefs, behaviors, stuff related to cancer. A lot of attitudinal stuff, a lot of beliefs kind of stuff. And when we pilot tested this with I think it was a Chamorro community, or Samoan community, a Tongan community, some of the questions didn't make sense to them. Hopefully, it's like, that doesn't make sense. We would never think of it that way. We would never say it that way. So we had to kind of change the wording a little bit for it to make sense to them to answer. Otherwise, it's really not applicable. Okay, so the answer is yes, you can if there was a good rationale. So that always gives you the idea that you should pilot test whatever you have with the population of interest, because to me this seems very straightforward, these questions, but to somebody else, depending on certain characteristics about them, it doesn't make sense, or they would answer it wrong because their meaning of it is different than what would have been expected. So you could alter, but then if you do that, what you should do is explain that in your method section. And basically you could say this particular questionnaire was adapted from blah, blah, blah. So adapted means you kind of changed it up a little bit. As needed, only as needed, based on pilot testing. Any questions? T-test calculator, covered that. Statistics, okay, so, yeah, we talked about all this, working knowledge, blah, blah. Percentiles. So we talked about frequencies and percentages for descriptive statistics. Another thing that you might come across with relative frequency is percentiles in the work you do. For example, you are the fourth tallest person in your group of 20. So do people know what percentiles are, by the way? Maybe you do know. This is just kind of, yeah, whatever. What are percentiles? If you took how many of you had to take a jury? Anybody have to take a jury? Well, what are examples of, I won't put you on the spot and ask you for your percentile, but what's an example of a good percentile for the GRE that was very desirable? What? 400. 400 for the percentile? Oh, 70 percentile? Oh, okay. Okay, what is 70th percentile? Yeah, so 70th percentile means that you did better. You got a higher score, as high or higher score than 70% of the people who took it that year. Very good. Sounds good, right? What would the 50th percentile be? The average and the median, basically the median, correct. So median is basically the middle point, the average score. Yep. If you ranked order them from lowest to highest, very good. Okay, so you come across, I think all of us who've had kids, you're very familiar with percentiles, right? Because, oh, my kid on the growth chart, right in the, they start to get worried when the kid is like a very low percentile because they're premature, and then, if they're really big, oh, my kid's in the 95th percentile, or whatever. So that's what percentiles are. And percentiles are based upon the normal distribution. So what happens is, what I'm basically saying is whatever percentile you are, you fit somewhere under this curve, right? And this is when they talk about a bell curve, this is a normal distribution. And what happens, and these are standard deviations. So like if you had a normal distribution and you had standard deviations above the mean, so these are, like this is one standard, we talked about what standard deviation is, right? How much how diverse the sample is. So if you're one standard deviation above the mean, this is where you are. If you were 2 standard deviations above the mean, and this is assuming if the data is normally distributed. 3 standard deviations above the mean, and then this is below average, right? 1, 2, 3. So it's symmetrical in the sense that it's mirror images of each other. The one half is a mirror image of the other. 0 would be the 50th percentile. It's right at the median. Okay? The mean, the median is all right there lined up here. When you're 1 standard deviation above the mean, what that means is that you're basically there's only 13.6% of people ahead of you, which means that you're in the 86 basically the 86th percentile, right? Which is pretty good. Well above average. You're 2 standard deviations above the mean. Well, that's there's only actually at this point there's only 2.5% above. It says 2.1% over here, but it's actually 2.5% over here. Well, 1.96, but so that means we're in the top 50 percentile. And then the opposite occurs in the other direction. So that's what percentiles are. It's how where you stand, where somebody stands relative to the population. Okay, that's what a percentile is. So when do percentiles reveal an abnormality? So when would you guys, as graduate students, be working with percentiles? Maybe if you're working a lot with kids, maybe you're looking at percentiles for, I'm thinking of language, right, for speech language pathology. You're thinking about percentiles for performance on speech and what's considered normal, what's considered, even for social work, same thing. What's considered normal in the range of normal and what's considered in the range of abnormal. These are, and there should be like a certain, it's not like everybody can fall exactly in the same place right in the middle, right? There's going to be, their normal is a little bit more above average and somebody else's normal is below average, right? But as long as they're not too far out either direction, they're probably okay. When it comes to clinical lab results, this was interesting. Okay, so I just happened to find something about sperm count, which I thought, okay, well, this turns out really well. This is a good visual right here in terms of percentiles. Or cutoff value, so they did sperm count, total count, how many of them are, I guess, moving around, and percentages, right? So what would be, so these are data, 50% would be the average, right? We can't expect every man to be somewhere here. This is like, whoa, they're really high functioning. And then there's people who are, I'm a little concerned about you. Oh yeah, these people go to the sperm bank, right? It's like, okay, I want this one, right? These people go home, we don't want those, okay? Or these people need help from these people, I don't know what, okay, whatever. So usually for clinical kind of results, clinical lab results, if anybody's below the 5th percentile, it's considered, let's look into this further, right? When it's the 95th percentile above, again, let's look into this further. It could be a potential problem. So for clinical results, that's just how percentiles work. And it's based upon this normal distribution, basically, right? Low sperm count over here, high sperm count over here. Everybody in the middle is kind of somewhere in here. Okay. this stuff is relevant for tests, this is relevant for clinical results, different things you can look at in terms of outcomes. All right. So when normal is not normal, examples of skewed data. So one thing about these kind of tests here that we talk about, any kind of continuous variable involved like t-test and over the correlation coefficient, the assumption is that the data is, if you had to plot it out, you'd have a normal distribution, not skewed like this. Okay, that's the assumption. Skewed means, well, it's not going exactly like, Pac-Man here. You may not know what Pac-Man is. You can play that those days. Okay. Positive skew is where there seems to be a tail of data to the right. And a negative skew is where there's a tail of data to the left. I'll give you an example. Real estate. You know why they do, when people talk about house of income, or like how many people have gone around shopping for a house? None of you did. Okay, or just looked around for fun, just looked at stuff. Looked at Zillow just for the heck of it. Okay, so what they have is, do they talk about mean income in the neighborhood, or not income, price? Or do they talk about median price? What do you think? Median, you know why? No, well, you know what? They're actually trying to be more reflective of what's selling. Because what happens if you get mean house price, what happens is if you go in a neighborhood track, like all the houses are about the same price, but then there's somebody who's got that primo nice house with all the fixing up with a pool. And so there would usually be a positive skew when it comes to median prices of houses. So that would be an example of a positive skew, because most people in a given housing tract, they're kind of here, plus or minus a few $1,000s. But then you've got the neighbor who you're jealous of, who's got all the walkman. You see that in the neighborhood, right? Sometimes you see like everybody's like, this is okay house. Boom, this house is so built up and big, and they got the, built it up and floor, an extra story, and they got the pool in the backyard. Yeah, all that stuff. So that's an example of a positive skew. And then on the other hand, you could have an example of a negative skew. This is probably the neighbor who has the neighborhood that has the neighbor who has a pink house. A bright pink, like fuchsia. And has her leaves going 6 feet tall, right? Okay, so that could be skeleton, So that's an example of a positive skew and negative skew. All right. Oh, and this is where we get, like if I was an artist, those look like lips there. Ooh, what's that? Okay, so how obesity status and income predict functional limitation onset. So I got this from, I thought it was a cool depiction here. And I gave you this handout, and I asked you to answer a few questions about it. Let's see if I have a copy for myself, because I forgot what I wrote. But I'm sure I had some great ideas at the time. Anybody have an extra copy somewhere? Oh, you have extra copies of the sheet? Oh, yeah. There you go. So let's take a look at this, and I want you to talk to your friends and.
What is that?
And tell me what these lips mean. Okay, so answer question 1, 2, and 3, and we'll go over this together. So this is an interpretation thing here. Totally, this is the test you could cheat. You could cheat all you want. And actually, there's actually number 4 in the back. So there's 4 questions: 1, 2, 3, and then 4 in the back.
Yeah.
Oh, yeah, and I put those arrows there in case you couldn't read this because it's kind of fuzzy. So 2 obese groups, 2 healthy groups, high income, low income, high income, low income. And they plotted it out to make that lovely picture. Oh, hey, what did you do? Yeah, thank you.
Sorry, I was mute.
No, what are you up to?
Meetings with reasons.
Oh, okay.
Good.
Good. I'm gonna have lunch, dinner.
Do you have things? Yeah. I'm gonna head out, just wanted to check in.
Yeah. Good.
And then John's gonna do it.
Yeah. Yeah. Well, good. You go home and whatever you gotta do, gotta do. Little chill.
Mona.
Okay. I was like, yeah. Or maybe
Well,
because it's like every week.
But 57, yeah. So it's not, it's like.
Okay.
Okay, thank you guys.
Well,
And then we're good for, second session. I think I'm.
Yeah.
Wait, is that helpful? Yeah.
Okay. Yeah. Fine. All right.
Thank you so much.
Thank you.
Okay.
Have a safe trip back home.
See you tomorrow. Bye.
When I start seeing people look up, I'll know that this is all done.
Okay, so you're right, so you're taking care of, we're right. Yeah, that'd be awesome.
These are like just
Yeah. This crowd's like, so whatever we say is ongoing. Carried over.
Yeah.
Oh,
Yeah.
That was on Yes, and that's what's been so all the ones that are people these yeah.
And then the engine is wide. If you look at the one that I it shows I mean, if you see the sheet, right? I love it. Right now. And those are the, so does it list? So those are the only ones that you need to be. Why?
So for this gift would be you and the second so I was in the middle of the process.
So I
I'm talking to you.
So they're only looking at this, right? So it is. I'm like, okay. I don't see the line.
Yeah, so I think like 15 to 20 years, but then the second time it's
Yeah.
Oh, how many more years above this, right?
I think it's just about like versus like other piece, right? And like how many more years of the functional limitations. So I was comparing like the 70-year-old, 70 years versus the 87 years, right?
Yeah.
Because it's like the obese and then healthy weight, and then one for the high income, right? So that's what I was looking at.
So we're looking at
Yeah, right. That's what I did, because you like graph.
Right.
That's only for the point, that's only at like 0.5, like at 50%. Like, are we talking about
Yeah.
probability, not just that probability? Because obviously, like, you know what I mean?
Yeah, we're just gonna kind of like. So we look at functional, we said, yeah, average years is 70 and 87.
How much more time do you need? You need till dinner time, no.
I'll be.
How about 2 more minutes?
Oh, wait.
2 minutes. 2 more minutes.
You're looking at these for like.
Question 4, see what question 4. Is between low-income groups?
Yes.
Yeah?
Yes.
Sorry.
You read my mind.
You just subtract.
Or like.
Yeah, we are.
Yeah, because that's the highest, right? Yeah, the bigger, and then.
Okay.
Oh, wait.
All right, let's congregate, let's congregate. All right, you ready? While you were doing all that, I was thinking about what I'm gonna eat. I want a grilled cheese sandwich if they can put tomatoes on it. That's what I like. But anyways, we'll see if they can do it for me. Or whatever they have, I don't know. Was this interesting? And this is real data. So, okay, so the association of body mass index with age of first onset of functional limitations. What are functional limitations? Does anybody know what they are? What are some functional limitations that people can encounter? Yes. Not being able to bend down. So basically activities of daily living. So bending down would involve probably tying your shoes, right? So that would be a functional limitation if you couldn't bend down well enough to tie your shoes would be one. What else? Walking. So like walking a certain number of feet would be one, right? What else? Can you think of other stuff? Pardon me? Getting dressed, taking a shower by yourself, eating by yourself, walking stairs by yourself, carrying a bag of groceries by yourself. Those are all things you need to be able to function, right? Being able to, even like getting into a bathtub kind of thing, right? Sometimes you might need that, or being able to even get into a car, right? Those kind of things. So that's what functional limitations are. And age. So we're using age of onset, probability, what else? Whether or not you're obese and what income you have, okay? So what age does each of the four groups? So we had 4 different groups, 2 obese groups and 2 healthy weight groups, and then they're high and low income. So low income is less than 25th percentile, so they're basically in the bottom 4th, right? And 75th percentile is the top 4th, right? And how they do in terms of onset. So the outcome of interest here is basically the onset. So what I did was basically come up with these questions. I just came up with them. And, it's just saying, well, there's a 50-50 chance at this point that you're going to have one of these physical limitations, right? So at what age does each of these 4 groups have a 50-50 chance of getting a functional limitation? So for the extremely obese, less than 25th percentile. So they're basically obese and low income. Is that a good combination? At what age do they have like a 50% chance, would you say? So that's the group that's obese. So that's the one, that's like the upper lip top, right? It's where you put your lipstick pencil there and start to draw, right? And so that group, the 50th percentile. So what age was that? So I would draw a dot right there where the 50th percentile is. So about what age is that? Around 60, what? 57, 60, around there, right? I would say just roughly speaking, 57, 60. I'm going to say 60 just to have a nice round number, okay? And then, so those are people who are obese, low income. How about obese, high income? 70. Okay, so that's obese, high income. So is that the lower lip? Which one is it? Okay, so it's this.
Purple one.
The purple. Okay. So 50. Okay, so the purple group is the second one. And so, yeah, when they got 50th percentile, yeah, roughly 70, I would say roughly, yeah, 70. We're not being exact here, but about 70, okay? So what would that tell me? Income has something to do with this, doesn't it? So maybe, if I was the same obesity level, but I was low income, I might have 10 less years of functional living, right? Just solely based on income. And why would that make sense if you had to think about why? Why would that be? Because maybe what you could afford, or you might have the right insurance to get what to help you? The right medication, right? What else? Yeah, probably the medication would be right. Probably be the main thing, right? Or if you pulled something, tore something, you might be able to get treatment, physical therapy for it, so that you're not, right? Okay. So how about healthy weight? 25th percentile, less than 25th. So you're healthy, but you ain't got much money. So then you're healthy. So that's the blue one? Is that the blue?
Yeah.
Okay. Healthy, low income, right? Where are you going to be at, roughly? What do you say, 75? Okay, 75. Yeah, let's say 75. All right. 75. Okay. How about healthy weight? And I'm doing all right. I've got a retirement plan going, got some decent income. On the last line, the bottom lip is my pencil, whatever lipstick thing. And I go over to, looks like over 90, right? 90, over 90, around there. I would say that's about, oh, well, maybe not quite 90. Yeah, let's just say almost 90, 88 years. Okay. All right. So pretty interesting, huh? So it's kind of telling you a few things, right? So income seems to matter, right? Because same weight status, regardless if you're healthy or obese, it seems like just income by itself adds some years of functional living, right? But with that, it seems like there's things that are a little bit more income. So maybe I can't control my income. Maybe I've got what I've got, you know. But what I can do is keep myself at a healthy weight, regardless of my income, right? That sure as hell, that really does help, doesn't it? Yeah. So it seems like both really matter, don't they? So are you better off having obesity with a high income? So if you had to pick, okay. So obesity with a high income, so the obese with a high income is the 70 years, right? Or having a healthy weight with a low income, what would you rather be? Oh, so money doesn't get me everything, does it? Because you know what? It seems as if, it seems like the better off people who are obese are actually have, just by nature of being obese, they have 5 less years than somebody who doesn't have as much income. So I would rather be the healthy weight with low income. Yeah, right? Because it seems like it's a 5-year, and so the Y is like the 5-year difference. Okay, so I mean, this has practical relevance. Okay, so we're looking at the numbers, so let's think about the practical relevance of this. Let's think about this. Let's say you're a doctor, and maybe somebody comes in and says, I don't give a crap what I eat because I don't have insurance to take care of myself anyway, so who cares? What would you say based on this data? Would you slap them in the face, and what would you say? You better live longer than my next person who has insurance, but they're a little overweight, right? Shame on you. You know, take care of yourself, right? What did you say? And then on average, how many more years of functional limitation does having a healthy weight have within the high income group? So within the high income group, we've got for obese, it's 70 years. For healthy weight, high income is 88. So that's a 13-year difference, right? 13-year difference in more function. And then with number 4, I meant to do it within the low income group. And so with low income group, you've got low income, you've got low income, you've got low income. Which one's low income? 60 years versus 75, so that would be like a 15-year difference in functional limitation. Yes, for number 3, what did you use? I did 88 minus 70. And then for the other one, I did 75 minus 60. So the moral of the story is both matter, right? And if anything, maybe the body weight is a little bit more important, but money sure does help too. Okay, so time for dinner. Yay! We're halfway through this. Thank you.